Now we're going to connect our theorem 424, the estimate for the summation of lambda of n divided by n for n less than or equal to x, to our function psi. And we're going to establish the following estimate for an integral involving psi. This estimate actually deserves a theorem, but unfortunately Hardai didn't consider this as a separate theorem. So in the future, I'm just going to refer to this as 22.6.1. To establish this, again we're going to use Abel's summation, or our theorem 421. Specifically, we're going to use the formula 22.5.2 in theorem 421, which says to use this formula, we'll set f of t equal to 1 over t, c sub n equal to lambda of n, c of x as a result will be the summation of lambda of n for n less than or equal to x, which is simply psi of x. And n1 is equal to 2. Actually, c of 1 is equal to lambda 1, which is by definition equal to 0. So these are the setups. As we cover more and more topics, you'll realize the importance of this Abel summation in analytic number theory. Because you will see a lot of transformations transforming arithmetic functions to the summation of those arithmetic functions. And this Abel summation provides a perfect bridge in many cases. So now let's continue. Now we simply plug in all these specific values for c sub n, f, etc. This is what we get. Now by theorem 414, we know that psi of x divided by x is bounded by a constant. And by theorem 424 above, we see the summation of lambda of n divided by n for n less than or equal to x equal to log of x plus big of 1. And now we're going to plug these two pieces of information back to this equation. And you will immediately see the integration from 2 to x of psi of x divided by t squared dt is equal to log of x plus big of 1, which finishes the proof of 22.6.1. You might wonder why we are proving this estimate for this integral of psi of t divided by t squared. And in particular, how is this relevant to the prime number theorem? Now let me show you how this could be relevant to the prime number theorem. Indeed, we have the following theorem that looks very much close to the prime number theorem. We'll show from this formula that lim_inf of pi of x divided by log of x is less than or equal to 1. But at the same time, lim_sup of pi of x divided by log of x is bigger or equal to 1. And you might think, because the prime number theorem concerns the limit of this ratio, are we able to obtain the prime number theorem immediately from these two inequalities? Unfortunately, no. We still need to show that the limit exists. As long as the limit of this ratio exists, it must be equal to 1. And that finishes the proof of the prime number theorem. So now let's prove this theorem for 26. We proved it by contradiction. We first recall by theorem for 20. We have pi of x similar to theta of x divided by log of x, which is again similar to psi of x divided by log of x. Therefore, to prove this theorem for 26, it suffices to show the lim_inf when x goes to infinity of psi of x divided by x is less than or equal to 1, and lim_sup when x goes to infinity of psi of x divided by x is bigger or equal to 1. It suffices to show these two inequalities. So now how do we prove them? Suppose that lim_inf as x goes to infinity of psi of x divided by x is something bigger than 1. For example, it is 1 plus delta for some delta bigger than 0. Note that delta must be a finite number because we already know that psi of x has the upper bound that is a constant multiple of x when x goes to infinity. So this delta must be a finite number as well. Then there exists an x0 bigger than 0 such that psi of x is bigger than 1 plus delta divided by 2 times x for all x bigger than x0. This is by the definition of lim_inf. Now let's look at the integral. We're going to split this integral into two parts. And the cutoff is this x0. Now, it is better to make this x0 bigger than 2, so that the first integral is always non-negative. In the second part, you see that when x0 is bigger than 2, which means when t here is bigger than 2, this psi of x has this lower bound. So we first throw away the first integral and you lower bound the second integral by what? By this linear thing applied to psi of t. But this guy is computable. It's equal to precisely, and from here you should be able to see a contradiction, because on one hand we just showed that this integral is log of x with coefficient 1 in the front plus big of 1, This is 22.6.1. On one hand, we have this. On the other hand, on the right-hand side, you get the coefficient strictly bigger than 1 times log of x. So there's a contradiction as x goes to infinity. Therefore, this contradiction shows the lim inf as x goes to infinity of plus fx divided by x must be bounded by 1. And the similar argument shows the lim sup is bigger or equal to 1. And that finishes the proof of theorem 426. And now you might ask, how far are we away from the final proof of the prime number theorem from theorem 426? It seems that it suffices to show this limit exists, because from this theorem, as long as the limit exists, the limit must be equal to 1. You might think we are really close, but unfortunately not, because the part that shows the limit exists is a truly technical part. And to that end, we'll need Selberg's asymptotic formula together with really hard analysis on the remainder term, by which we mean psi of x minus x. And that is the true difficulty and technicality in proving the prime number theorem.